Alright, this last video in the circles unit is designed to give you some practice writing some circle proofs so that you'll become a little bit more fluent with it and feel a little bit more comfortable with them by the time you come to your exam. So why don't you go ahead, take a look at the first example, mark anything that you can mark in the diagram, and think about a strategy that you might use in order to prove those two angles congruent to each other. And I'm going to give you a few seconds to think about this. When I first look at what it is that we're trying to prove, angle O congruent to angle P, the first thing that comes to my mind is that if I could get these two triangles congruent to each other, I could use CP/CTC in order to show that their angles are congruent. Now that said, because this circle O looks or appears to be larger than that circle P, and I don't have any pairs of sides congruent in these triangles, nor do I have a way to show any congruent, I'm thinking that although that was a good idea, it might not be necessarily the right way to proceed with this problem. So now I'm back at square one, and I'm thinking, well, if I could get these two triangles similar to each other, then that would also show that their angles are congruent to each other. And in looking at the picture, I can see a pair of vertical angles there at B. So if I could only get one more pair of angles congruent to each other, I would have what I need to show that the triangles are similar. Now this AC being tangent to the circle, remember we have a theorem that says anytime that you have a tangent line that meets a radius, the result is that they're always perpendicular to each other. So where tangent AC meets radius OA, there's a right angle formed. And likewise over here in this other circle, where tangent AC meets radius PC, there's a right angle that's formed. Now I've got two angles in the triangle on the left congruent to two angles in the triangle on the right, forcing those two triangles to be similar to each other. So that's the direction or the gist that I'm going to take with this proof. Somewhere in my proof, I need to write about angle A being congruent to angle C, and the way I'm going to get there is to start with that tangent line. So where I'm going to start writing my proof is with that tangent line. So I'm going to start by talking about segment AC, being tangent to circle O at point A and to circle P at point C. And I know that when a tangent and a radius intersect, the result is always perpendicular. So I'm going to say that tangent AC is perpendicular to radius OA. And in a similar fashion over here in the smaller circle, that tangent AC is also perpendicular to radius PC. I'm going to say a radius drawn to a tangent is perpendicular to that tangent. And then because I know that perpendicular lines make right angles, it tells me that angles A and C are both right angles. And since right angles are always congruent, from there I can say that angle A is congruent to angle C. Now remember that my goal in trying to show these two guys similar was to get a pair of congruent angles. Up until now I've written about one pair of angles congruent. To see which other pair I was going to use in my proof, I'm going to backtrack back to my picture. So in my picture, I noticed that I had also marked those vertical angles at point B congruent. So that I can write about them in my proof, I'm going to label them 1 and 2 Then I'm going to scoot back down here, and I'm going to write about angle 1 being congruent to angle 2. I know they're congruent because they're vertical angles. So now that I've written about two pairs of congruent angles, I'm all set up to go ahead and write about my triangles being similar to each other. When I name those triangles, I'm going to be very careful to name their vertices in corresponding order. Since A in the triangle on the left corresponds to angle C in the triangle on the right, I'm going to start by naming that second triangle with a C, followed by a P and a B. And that is angle-angle similarity. And once I know those two triangles are similar to each other, I know two things. I know that all their corresponding sides are in proportion. That's not what I'm looking for in this case. I know that all their corresponding angles are congruent to each other, which is what I'm looking for in this proof. So I'm just going to say similar triangles have corresponding angles that are congruent. All right, all is said and done. At this point, if you have questions about this problem, why don't you make a note to yourself in your notes so that you can remember to ask me about it the next time that you come back to class. And with that said, I'm going to go ahead and flip up to the top of the next page. Like the first example, I'm going to give you a few seconds to go ahead and mark your diagram, take a look at what's being asked of you in the problem, and how you can use the information that's been given to you together with the diagram to kind of put together some thoughts or strategies as to how we might show what it is that we're being asked to prove. All right, so when I first see this proof, these segments being multiplied together, the first thing that comes to my mind, and hopefully yours too, is that I'm going to have to prove that a pair of triangles here is similar. As far as which triangles it is that I want to prove similar, I'm going to go get my highlighters out, and at home you should be getting your highlighters out too so that you have some practice doing this so you're not doing it for the first time when you get to a quiz or a test. So I'm going to start by highlighting that first segment, AD. And that first segment is in the big, or part of the big triangle. My second segment, and I have a typo on my paper, although yours is correct, this should say DC. When I go look at DC, segment DC is a segment in the big triangle. Segment DC is also a segment in one of the smaller triangles. So I'm going to kind of put that on the back burner for a minute and go look and see what I find when I look at the other guys. AC, the only triangle that AC is a segment in is the large triangle, so I'm going to highlight the same color as I highlighted AD. And then DB, the only segment that's a triangle that's a segment in is this smaller guy, or one of the two smaller guys. And then my last remaining one is DC. So in looking what I've highlighted, I've got these two guys right here. I'm going to put a third one in there to build a triangle. And looking at the yellow ones, I'm going to do the same thing. Put a third one in to make a triangle. And now I understand what's going on a little bit better in this problem. I'm trying to get my big yellow triangle similar to my smaller purple one. And in looking at the problem, the first thing I notice is that these two triangles share angle C. Angle C has to be the same in the purple triangle as it is in the yellow one. So by the reflexive property, angle C is congruent to itself. And now I'm looking for a second pair of angles. And this pair of angles is going to be a little bit more difficult to find, so I'm going to have to be a little bit smarter about it. If I look at tangent AD is this guy right here. And if I remember that theorem that I used in my first proof, that any radius drawn to a tangent is always perpendicular at that point of tangency, I know that that angle ADC has to be a right angle. The other thing that I'm going to pay attention to, if I look at this arc down here, this green arc represents half of a circle, or a semicircle. Angle B is inscribed inside that semicircle, and therefore his angle measure will be half of the 180, or 90 degrees, making angle B a right angle. So now I've got a right angle in the purple triangle congruent to a right angle in the yellow triangle. I also have angle C in the purple triangle congruent to angle C in the yellow triangle. That therefore gives me the two pairs of congruent angles I need to make the yellow triangle similar to the purple triangle. So that's going to be kind of the direction or the framework for this proof that I'm going to write. Because the right angles are the more challenging part of the problem, I'm going to start out by writing about the right angles. So I knew those guys were right angles, or I knew one of them was a right angle because of the fact that the tangent met the radius. So I'm going to start talking about the tangent, the diameter, and the secant is kind of excessive information. We really don't need that for our proof, but I'm going to toss it in there just for good measure. So those are our givens. Because AD was a tangent, and I know that where the radius meets the tangent, they form perpendicular, or they are perpendicular, I can go ahead and say that OD, radius OD, is perpendicular to tangent AD. And that's because a radius drawn to a tangent is always perpendicular to that tangent. Although I might be tempted to say that angle D is a right angle, if I look in the picture, there's a couple different angle Ds, so I need to be a little bit more clear and specific about exactly which angle D I'm referring to. So I'm going to call that angle by its formal name, angle ADC. And that's because perpendicular lines make right angles. I also need to talk about this angle up at B being a right angle. And like that angle at D, I have to call him by his formal name because in that picture there is more than one angle B. I know that he's a right angle because he's an angle inscribed in a semicircle. So I'm going to call him angle DBC. And again, I know he's a right angle because an angle inscribed in a semicircle has to be a right angle. So now I've got a couple of different right angles. I know that all right angles are congruent to each other. I can go ahead now and say that these two guys are congruent. And remember that my goal or my mission in writing this similarity proof was to show that I had a couple different congruent angles. So at this point, I've written about one of them. So there's my first pair of congruent angles. I'm going to zip back to the top of the page so that I can consult the diagram and see what else it is that I need to write about in this proof. So if I come back up to the top of the page, I notice that in my picture I had marked angle C congruent to itself. So that's the next thing that I want to write about in my proof. And I know those two guys are congruent to each other because of the reflexive property. And that's my second pair of congruent angles, so I'm going to mark that with an A. Now that I've got my two pairs of congruent angles, I'm all set to say that my triangles are similar to each other. Like the first proof that I wrote, when I name these two similar triangles, I'm going to be very careful to match up their corresponding angles. So triangle ADC similar to triangle DBC. That's angle, angle, similarity. Once the triangles are similar, I know that all their corresponding sides are in proportion. So I know that if I compare sides AD and AC from the first triangle, that's going to be the same as if I compare sides DB and DC in the second triangle. And I picked those sides simply by looking at the sides that I needed up here for my proof. So I'm just going to say similar triangles have corresponding sides that are in proportion. And now to obtain what it was that I was trying to prove, I'm simply going to take my proportion, and I'm going to do with my proportion the same thing that you've been doing with proportions since 7th grade, and that's cross multiply. So my cross product going in one direction, AD times DC, has to be equal to my cross product going in the other direction, AC times DB. And very simply, that is cross multiplication. If you want to get fancy with it, you can say the product of the means is equal to the product of the extremes. But I'm a big fan of the keep it simple method. Just say that it's cross multiplication. Now, like with the first proof, if there's anything in this one that doesn't feel right or you don't understand, please do make a note of it to yourself so that you can remember to ask about it the next time that you come to class.